A cement is a binder, a substance that sets and hardens and can bind other materials together. The word cement can be traced back to the Roman term opus cimentitium, used to describe masonry resembling modern concrete that was made from crushed rock with burnt lime as binder. The volcanic ash and pulverized brick supplements that were added to the burnt lime to obtain a hydraulic binder were later referred to as cementum, cement, and cement. Cements used in construction can be characterized as being either hydraulic or non-hydraulic, depending upon the ability of the cement to set in the presence of water. Non-hydraulic cement will not set in wet conditions or underwater. Rather, it sets as it dries and reacts with carbon dioxide in the air. It can be attacked by some aggressive chemicals after setting. Hydraulic cements set and become adhesive due to a chemical reaction between the dry ingredients and water. The chemical reaction results in mineral hydrates that are not very water-soluble and so are quite durable in water and safe from chemical attack. This allows setting in wet condition or underwater and further protects the hardened material from chemical attack. The chemical process for hydraulic cement found by ancient Romans used volcanic ash with lime. The most important uses of cement are as a component in the production of mortar in masonry, and of concrete. A combination of cement and an aggregate to form a strong building material. Chemistry. Non-hydraulic cement, such as slate lime, hardens by carbonation in the presence of carbon dioxide which is naturally present in the air. First, calcium oxide is produced by lime calcination at temperatures above 825 degrees Celsius for about 10 hours at atmospheric pressure. CaCO3 Cal plus CO2. The calcium oxide is then spent mixing it with water to make slate lime. Cal plus H2O California 2. Once the excess water is completely evaporated, the carbonation starts. California 2 plus CO2 CaCO3 plus H2O. This reaction takes a significant amount of time because the partial pressure of carbon dioxide in the air is low. The carbonation reaction requires the dry cement to be exposed to air. For this reason, the slate lime is a non-hydraulic cement and cannot be used underwater. This whole process is called the lime cycle. Conversely, hydraulic cement hardens by hydration when water is added. Hydraulic cements are made of a mixture of silicates and oxides, the four main components being belite, alite, tricalcium aluminate, brown millerite. The silicates are responsible of the mechanical properties of the cement. The tricalcium aluminate and the brown millerite are essential to allow the formation of the liquid phase during the kiln sintering. The chemistry of the above-listed reactions is not completely clear and is still the object of research. History. Alternatives to cement used in Antiquity. Cement, chemically speaking, is a product including lime as the primary curing ingredient, but it is far from the first material used for cementation. The Babylonians and Assyrians used bitumen to bind together burnt brick or alabaster slabs. In Egypt, stone blocks were cemented together with mortar, a combination of sand and roughly burnt gypsum, which often contained calcium carbonate. Macedonians and Romans. Lime was used on Crete and by the ancient Greeks. There is evidence that the Minoans of Crete used crushed potsherds as an artificial pozzolan for hydraulic cement. It is uncertain where it was first discovered that a combination of hydrated non-hydraulic lime and a pozzolan produces a hydraulic mixture, but concrete made from such mixtures was used by the ancient Macedonians and 3 centuries later on a large scale by Roman engineers. There is a kind of powder which from natural causes produces astonishing results. It is found in the neighborhood of Baiae and in the country belonging to the towns round about Mount Vesuvius. This substance, when mixed with lime and rubble, not only lends strength to buildings of other kinds, but even when piers of it are constructed in the sea, they set hard under water. Marcus Vitruvius Pollio, Liber 2, De Architectura, Chapter 6, Pozzolana, Sec. 1. The Greeks used volcanic tuff from the island of Thera as their pozzolin, and the Romans used crushed volcanic ash with lime. This mixture was able to set under water, increasing its resistance. The material was called pozzolana from the town of Pozzuoli, west of Naples, where volcanic ash was extracted. In the absence of pozzolanic ash, the Romans used powdered brick or pottery as a substitute, and they may have used crushed tiles for this purpose before discovering natural sources. Near Rome, the huge dome of the Pantheon in Rome and the massive baths of Caracalla are examples of ancient structures made from these concretes, many of which are still standing. The vast system of Roman aqueducts also made extensive use of hydraulic cement. Middle Ages. Although any preservation of this knowledge in literary sources from the Middle Ages is unknown, medieval masons and some military engineers maintained an active tradition of using hydraulic cement in structures such as canals, fortresses, harbors, and shipbuilding facilities. Cements in the 18th century. Technical knowledge of making hydraulic cement was later formalized by French and British engineers in the 18th century. Tabby, a building material using oyster shell lime, sand, and whole oyster shells to form a concrete, was introduced to the Americas by the Spanish in the 16th century. John Smeaton made an important contribution to the development of cements while planning the construction of the third Eddystone Lighthouse in the English Channel, now known as Smeaton's Tower. He needed a hydraulic mortar that would set and develop some strength in the 12-hour period between successive high tides. He performed experiments with combinations of different limestones and additives, including trash and pozzolanas, and did exhaustive market research on the available hydraulic limes, visiting their production sites, and noted that the hydraulicity of the lime was directly related to the clay content of the limestone from which it was made. Smeaton was a civil engineer by profession, and took the idea no further. In the South Atlantic seaboard of the United States, tabby, relying upon the oyster shell middens of earlier Native American populations, was used in house construction from the 1730s to the 1860s. In Britain particularly, good quality building stone became ever more expensive during a period of rapid growth, and it became a common practice to construct prestige buildings from the new industrial bricks, and to finish them with a stucco to imitate stone. Hydraulic limes were favored for this, but the need for a fast set time encouraged the development of new cements. Most famous was Parker's Roman cement. This was developed by James Parker in the 1780s, and finally patented in 1796. It was, in fact, nothing like material used by the Romans, but was of natural cement, made by burning septaria, nodules that are found in certain clay deposits, and that contain both clay minerals and calcium carbonate. The burnt nodules were ground to a fine powder. This product, made into a mortar with sand, set in 5 to 15 minutes. The successive Roman cement led other manufacturers to develop rival products by burning artificial hydraulic lime cements of clay and chalk. Roman cement quickly became popular but was largely replaced by Portland cement in the 1850s. Cements in the 19th century, apparently unaware of Smeaton's work. The same principle was identified by Frenchman Louis Vicat in the first decade of the 19th century. Vicat went on to devise a method of combining chalk and clay into an intimate mixture, and, burning this, produced an artificial cement. In 1817, considered the principal forerunner of Portland cement, and Edgar Dobbs of Southwark patented a cement of this kind in 1811. In Russia, Egor Shalev created a new binder by mixing lime and clay. His results were published in 1822 in his book A Treatise on the Art to Prepare a Good Mortar, published in St. Petersburg. A few years later, in 1825, he published another book, which described the various methods of making cement and concrete, as well as the benefits of cement in the construction of buildings and embankments. James Frost, working in Britain, produced what he called British cement, in a similar manner around the same time, but did not obtain a patent until 1822. In 1824, Joseph Aspdin patented a similar material, which he called Portland cement, because the render made from it was in color similar to the prestigious Portland stone. However, Aspdin's cement was nothing like modern Portland cement but was a first step in its development, called a proto-Portland cement. Joseph Aspdin's son William Aspdin had left his father's company and in his cement manufacturing apparently accidentally produced calcium silicates in the 1840s, a middle step in the development of Portland cement. William Aspdin's innovation was counterintuitive for manufacturers of artificial cements, because they required more lime in the mix, a much higher kiln temperature, and the resulting clinker was very hard and rapidly wore down the millstones, which were the only available grinding technology of the time. Manufacturing costs were therefore considerably higher, but the product set reasonably slowly and developed strength quickly, thus opening up a market for use in concrete. The use of concrete in construction grew rapidly from 1850 onward, and was soon the dominant use for cements. Thus Portland cement began its predominant role. Isaac Charles Johnson further refined the production of Meso-Portland cement and claimed to be the real father of Portland cement. Setting time in early strength are important characteristics of cements. Hydraulic limes, natural cements, and artificial cements all rely upon their belite content for strength development. Belite develops strength slowly, because they were burned at temperatures below 1250 degrees Celsius. They contained no alate, which is responsible for early strength in modern cements. The first cement to consistently contain alite was made by William Aspdin in the early 1840s. This was what we call today modern Portland cement. Because of the air of mystery with which William Aspdin surrounded his product, others have claimed precedence in this invention. But recent analysis of both his concrete and raw cement have shown that William Aspdin's product made at Northfleet, Kent was a true alite-based cement. However, Aspdin's methods were, rule of thumb, Vickett is responsible for establishing the chemical basis of these cements, and Johnson established the importance of sintering the mix in the kiln. In the U.S., the first large-scale use of cement was Rosendale Cement, a natural cement mined from a massive deposit of a large dollar-stone rock deposit discovered in the early 19th century near Rosendale, New York. Rosendale cement was extremely popular for the foundation of buildings and lining water pipes. Sorel cement was patented in 1867 by Frenchman Stanislas Sorel and was stronger than Portland cement, but its poor water restive and corrosive qualities limited its use in building construction. The next development with the manufacture of Portland cement was the introduction of the rotary kiln, which allowed a stronger, more homogeneous mixture and a continuous manufacturing process. Cements in the 20th century. Calcium aluminate cements were patented in 1908 in France by Jules Bede for better resistance to sulfates. In the U.S., the long curing time of at least a month for Rosendale cement made it unpopular after World War I in the construction of highways and bridges, and many states and construction firms turned to the use of Portland cement. Because of the switch to Portland cement, by the end of the 1920s, of the 15 Rosendale cement companies, only one had survived. But in the early 1930s it was discovered that, while Portland cement had a faster setting time, it was not as durable, especially for highways, to the point that some states stopped building highways and roads with cement. Bertrand H. Waite, an engineer whose company had worked on the construction of the New York City's Catskill Aqueduct, was impressed with the durability of Rosendale Cement, and came up with a blend of both Rosendale and synthetic cements which had the good attributes of both. It was highly durable and had a much faster setting time. Mr. Waite convinced the New York Commissioner of Highways to construct an experimental section of highway near New Paltz, New York, using 1 sack of Rosendale to 6 sacks of synthetic cement. It was proved a success, and for decades the Rosendale synthetic cement blend became common use in highway and bridge construction.